Hi again, I'm John from Optics for Hire, and with me is Sergey Sidorovich, also from Optics for Hire. Hi Sergey, how are you doing?
Hi John, I'm fine, thank you.
Sergey and I have been doing these presentations a couple a week, talking about what optical engineers actually do with their time. And Sergey has been working as an optical engineer for quite a few years. I won't say how many exactly, but he's extremely experienced and has worked on all kinds of different programs and projects. And today what we're going to talk about is a request that we get with some frequency about the design of a short throw projection system. If you're interested in optical engineering content, please like and subscribe. And don't forget to comment below. We always appreciate hearing from you, and it helps the algorithm. Thanks. So there are applications, maybe projecting images on a building, projecting images on a moving vehicle is one that people asked about, projecting images on a wall from a very short distance away, where there just isn't space to use a full kind of off-the-shelf projector that you would see. So short-throw projectors are a market niche, and there are methods and methodologies for designing them. So we're going to talk today about a project that Sergey worked on, and we'll show one of the concepts that's used in short-throw projection systems. So Sergey, I'm seeing here since September 2019, so I'm definitely testing your memory here, since that was 6 years ago from the recording date. But let's look at what we have here. So Sergey, talk me through this first, what the layout is, and then we'll talk about this. So what is the system that we're trying to create here?
Well, you can see on the right side this small rectangular is the projector placement.
Okay.
And it is extremely small for such tasks. This was one of the aims of this project, and it placed, you can see that it is placed not in the center of projection as we usually see. It placed somewhere on the side of the projection, and I can say that it is placed in the corner of the projection.
So in this system, the viewer would be here, and this is sort of the screen, the wall that's being used, and this could be from above, I guess. It could be from the side, but we have this very small lens and this large projection screen, and the people look at it from here. And I would say, what are the goals before we talk about this? Why isn't this easy? So what are you trying to accomplish here? Is it distortion? Is it resolution? Is it something else?
You're absolutely correct. Two main goals for such system is to compensate distortion and achieve high resolution.
And what about chromatic aberration? Is that likely to be one that we would see in a system like this, or is that not as much of a factor?
As usually, we are reviewing the chromatic aberrations as a part of the resolution. It makes chromatic aberrations usually makes resolution worse. So yeah, it is also issue for this project, for this system, but it is a part of the resolution task.
Okay, so we'll look at specifically what we're looking at here. You are, I think we'll show on the next screen, but you created kind of a virtual image of just font text that we could create at the image plane, which is a DMD, I should say, right? So and then you wanted to see, how distorted would it be by the time it was projected around this wide angle and short throw. Is that right? So this is the normal image at the focal point.
This is a simple image.
Okay.
Which resolution corresponds to the DMD resolution.
DMD resolution. Okay. So then we're going to see, well, what does it look like when it gets here? So now this is our projection engine. This is some lenses, which I'll have you explain. Just before we get into that, what are the different color lines? Is this different colors of wavelength or different parts of the image? What is this?
In simple words, these are different spots in the DMD. We can use different spots in the image to estimate quality or distortion or something else. Usually we use some center spot in the center. As a rule, this is the higher quality spot. Angles and some spots around between the angles and the center of the image to see quality of the image in these spots. Because
each line is a different part of the display, which is going to a different
Spot.
different
Different
location.
spots in
Yeah.
this case.
Okay. So now one thing I notice about this is just a concept stage. I'm noticing these all seem to be spherical elements. Am I right about that?
at this moment, yes, these are spherical elements.
And why did you start there? Is that easier for a concept design than sort of highly complex aspherical elements? Okay.
It is faster for concept.
Okay.
We divide project in several stages, and as a rule, the first stage we need to make some feasibility. We need to find out is this feasible to achieve requirements that the client wants, and using of the spherical surfaces is the most quick way to do this. One more trick in this: if we are able to achieve some quality with help of spherical surfaces, it means that we will able to improve it with help of aspherical surfaces.
It's not going to get harder to get good
Yeah.
image quality. It's going to get easier.
And from another side, if we will use some kind of complex aspherical surfaces here and we will achieve some quality, it is not a guarantee that this design with aspherical surfaces will feasible in production. It is also possible that such design will require extremely tight tolerances for production. And
So if you let ZMAX just use the aspherical surfaces, you might get something that, quote, works, but would be completely unmanufacturable. And you avoid that risk by this approach you took.
yes, if spherical surfaces works and provide nearly suitable quality, it means that in the design we can improve it with help of spherical surfaces or add some kind of aspherical lenses somewhere to improve quality, tolerances, and something else inside the design.
So we'll look at this one again. This is just the test image that you're putting at the Texas Instrument DMD at the focal plane. And it's 192 by 1080.
This is a simulation of the DMD. This slide, let's call it slide. Its slide size of this slide will correspond with the DMD size, and its resolution is the same as DMD resolution. So I place this object instead of DMD in the model.
So now we have a more close lookup of or close image of your optical system. We can see a little more what's going on. So here's the DMD. We have a beam splitter and then the lens. And now this mirror seems like it's important. Tell us about how the whole system works, how the mirror relates to the lens and the rest of the elements.
It is interesting. You can see that at the left side, color lines are only in the bottom of the projector. It really corresponds to such projector's design. The image source is placed not in the center of in the optical axis. It is placed or at the bottom side or even on the quarter of the optical path of the system. And it means that only half of a lens or even less part of lens will work in this case. Effectively works with the radiations that that this system produces. And light beams moves from left side through the beam splitter that is part of the light engine through the lenses, and the lens forms not the image, it forms light beams suitable for the aspherical mirror, and aspherical mirror is the last and final step for this system. It first of all fixes distortion, it corrects distortion, and also it helps to focus different parts of the projection in their places.
Let me ask maybe a dumb question. So the bottom of the lens here, is this in a real design, would this be cut off because these rays aren't being used, or are you just doing half of it? I mean, I heard you say that the DMD is only using half of the image, is using only about half of where the image plane would be. So if you were to formalize this design, are there rays, is there light coming out this direction that you're just not showing in this picture, or would we maybe be able to cut, we could just cut these off, right? We could just...
Yeah,
okay.
We can cut them to save place.
Got it.
And mass.
Same space. Okay, interesting. All right, well, let's see how you did, or how we did. This is now the image plane. So now we're looking at a virtual image here, and this is a 2 meter projection area coming out of this small projection system. And this is what...
2 meter per 1.12 5 meters. Yeah, this is the size of the
meter. 2 meters by 1.1 meter. And we have these little 10 millimeter letters, which you nicely expanded. And what I noticed is that in the center, it's definitely white. The resolution looks very good. In the corners, I can still read everything. I'm seeing a little distortion here, and I am noticing some different colors showing. What are your thoughts on this image that we're seeing here?
This is distortion and chromatic aberrations, but concept shows that it is feasible task to achieve high resolution with this kind of projector and this size of the projection, because we have extremely small distance between the projector and the projection plane, and we can achieve very big projection and leave pretty high resolution for it. And it means that further work on design can save resolution that we see in the center.
We can get better with design optimization, but we know that in general you can have something that's quite small.
Spherical lenses.
Yeah, a lot of options. So in that, I think that was your conclusion. You're mentioning something here about a concave mirror versus a convex mirror in the conclusion. I don't quite follow that. Were you experimenting with different mirror shapes here?
Yes.
So this is your convex mirror, I guess, is that right? And the concave mirror is what you're showing, is that right? And then the convex mirror, you said, was worse.
Yeah, but the mirror also will be cutted, and the final form will not look like convex or concave form. It will look like strange, but it will work.
Well, thanks, Sergey. This was interesting. I hope it was interesting to our viewers, who hopefully will comment below. But thanks for your time in explaining the work of Optical Engineers and what you did to prove out a concept for a sort of ultra short throw projector. Thanks again, Sergey.
Thank you, John.
Thank you. Have a great day. See you. Bye-bye.
See ya. Bye.